Good afternoon. You are welcome to the third week of the facilitation. I hope you are all getting used to the content of the courses. Um, Last week, we discussed to some extent concerning function of complex variable. So we continue from where we stopped last week and also try to discuss Cauchy sequence, which is what we are supposed to discuss for the third week. So at the end of the class today, I will send you this lecture note, which we are going to use for today's class. So last week, we have established the concept of complex number. So this week, we go ahead to look at another idea or another area of complex number, which has to do the modulus and argument of complex number. So the modulus of complex number is defined as this, which is z. We all know that z is used to represent complex number, which is z is equal to the square root of x squared plus y squared. So x here is the real part of the complex number, while the y is the imaginary part. So if you have it this way, you have what we known as the modulus. So the argument is written as argz, which is equal to the arctan of the value of y divided by the value of z. So if you are asked to compute the modulus given a complex number, you apply equation 1. If you are asked to compute the argument of a complex number, you use equation 2. Hope that is clear. Now, another concept that we need to know is what is known as complex conjugate. The complex conjugate is defined as z star is equals to x minus iy. We know that normally z is equals to x plus iy. So when you now take the complex conjugate, you only change the sign, the positive sign to the negative sign. That's why you have z star is equals to 6. So if you have this, there are a lot of rules that holds. So one of the rules is what we have in equation 3, whereas if you have z and you use z to multiply the conjugate of z, you are going to have the square root of the square, the square of the modulus. That is, by the time you take the modulus of z, then you square it, you have z and z conjugate. The same thing, if you have z plus z1, we are given two different complex number, which are z1 plus z2. So if you add them together and you take the conjugate, you can write it in this form: the conjugate of z1 plus the conjugate of z2, which is equation 4. The same thing, if you have it in multiplication form, z1 times z2, then you take the conjugate, it will be conjugate of z1 times conjugate of what? Z2. So now, if you have z1 over z2, that is division now, this you can write it in this form. Likewise, if you have the double conjugate now, you have the conjugate of z and you also have the conjugate of the conjugate again now, you have it to be z. So another concept, another equation useful to us is when you have z plus z conjugate, it will be 2 times the real part of z, which is equals to 2x. And we know that the real part of z is x. Then you just multiply by 2. And that is equation 8. Any question on that? Any questions? Anybody ask questions? Okay, fine. Let's continue. Now, if you have it to be z minus z conjugate, that one is just 2i, the imaginary part of z, that is 2i, then times, we know the imaginary part of z to be y, that is 2i times y. So these are another good equations or another properties that's of importance to us when you are dealing with complex number. The same thing, when you have z divided by z conjugate, you can write it in this form, because we know z itself is equals to this. Now, divided by this now, it will give you this expression. Please take note of all this relationship, because it will help you to be able to demystify a lot of problem under complex number. Now, another thing that is of importance to us again is what we know that the polar representation of complex number. That is, when you represent complex number in a polar form, you know, earlier on we said that z is equals to x plus iy, but if you are taking it to polar coordinate now, it will be z is equal to r exponential I theta. Here r and theta are real. So the same thing, we can take the modulus. The modulus of z now is what we know as r now in this case. So theta is now the argument that we have discussed earlier on. Hope you are getting it. So now, if you now have exponential high theta now, we can write it as this. Exponential high theta is now equal to cos theta plus I sine theta. This is when you put complex number in a polar coordinate representation. I hope I'm making sense. If you have any question, you can ask me. So any questions? Okay, fine. If there's no questions, so we move to the next thing that we are supposed to have discussed last week, but because of time we couldn't reach there, is theorems of limit of function. So now, what is limit? So limit are used to describe the value of function at a certain input in terms of its values at nearby input. There are some rules for computing limit. One of them is when you have lim of c, that is when s tends to a, it is just the constant, because c here is a constant, just the constant that you just take. So now, the same thing, when you have lim of s when s tends to a, where you see x, you put the value of a, and the answer is a. So another one is when you have limit of cx as s tends to a, you can write this as c, which is a constant, you bring it out, limit of x as s tends to a. So where you see s, you put a. So in that case, you have the limit. Another function is this. When you have the limit of f of s plus g of x as s tends to a, this you can write it as a singular entity, which is equals to limit of s tends to a of s plus limit of s tends to a of g of x. The same thing when you have multiplication, limit of s tends to a of f of s dot g of x. You can write this as the limit of s tends to a of f of s then times the limit of s tends to a of g of x. So likewise, you can do the same thing for limit of s tends to a of f of s divided by g of s, which can be written in this format. Let's look at some example to be able to get more information as regards to this. Now, if you look at this now, the first rule here, which is limiting of c tends to c. Wale, Moshi Warand. So an example is when you have the limit of 4 of s tends to 2. So in this case now, because 4 here is a constant, s is not there, so the answer is 4. Since 4 is a constant, the limit of 4 as x approaches 2 is 4. Now, when you look at the second one here, the limit of x is equals to a as s tends to a. Where you see s, you put the value of a. Now, here now we have s tends to 10. When you replace x here with 10, the answer is what? 10. Now, when you look at this now, this is another one which we just discussed. And a good example is limit of 6x. So as s tends to 2, 6 here is a constant, you take it out. Then limit of x, where you see s, you put 2. Then it will now be 6 times 2, which is 12. So the other one is this now, that when you have f of s plus g of s as s tends to a good example is limit of x 5x squared plus 3x. So in this case, this will be your f and this will be your g of x. So if you split them now, it will be, if you apply this rule on this now, it will be 5 limit of s squared of s tends to 2 plus 3 limit of x as s tends to 2. So where you see s, you put 2. It is x squared, which is 2 squared, then times 5, you get 20. The same thing here, you get it, then you add it to give you 26. The same thing with the multiplication, which is a good example is this. By the time you apply that procedures like I did here, you realize that this 3x squared dot 8s, the answer is 192. So the same thing with f of s over g of s as s tends to a. So the limit of f of s of this now, a good example is 3s over 6. So as s tends to 2, so you can write it. This is a limit, then this is a constant now, limit of this. So 3 times 2, because the limit of where you see s, you put 2, you have it as, and this is a constant is 6, the answer is 1. So another function, another useful function is this now, which is limit of the square root of n of f of x. We can write it as s tends to 8, it is the square root of limit of f of x. The same thing here, when you have the limit of f of x all to power of n as s tends to a, This you can also write as limit of this altogether to the power of n as s tends to a. So I will expect you to look at this problem. Then I want you to solve all this problem yourself. The first example here say find the limit of the following function. So the limit of 6 of x as s tends to 2. The limit of 4x squared dot 2s as s tends to 3. Then the limit of 5x over 6 as x tends to 3. Then the limit of 3x squared plus 5s as s tends to 2. Then the limit of the square root of 2 roots x squared plus 3x as s tends to 3. So you are expected to solve this 5 problem using the rules that we have just discussed. About 9 or 10 rules that I just given to you. Apply them to solve this problem. Once you are able to do that, then you are confident enough that you can solve problems that has to do with limit. Any question on that? So now, any question? Okay, fine. Now, let's look at another examples as regards to what we have discussed. I say, given that z1 and z2 are complex variable, then z1 is equal to x1 plus iy1, then z2 is s2 plus iy2. Now the question is that obtain an expression for z1 plus z2, then the conjugate of z1 plus z2, and the conjugate of z1 plus z2, and this z1 dot z2. So the second question is if z is equal to 0, then it has a complex inverse of this, so that this is equal to this if z is equal to a plus ib. So in solving this problem, we are expected to use all these rules stated here, all these ones. You have to expect to apply some of these things to solve the problem. So now let's look at the solution. Now the first one, we say that z1 is equal to x1 plus y1, then z2 is equal to x2 plus iy2. So if you are to add it, this is z1, this is this. You only take those that has something in common. For the z1, this is the real part. For the z2, this is the real part. You bring the two of them together, s1 plus s2. For the z1, this is the imaginary part, and for the z2, this is the imaginary part. You take them together, you have it y1 plus y2 I. So now you have solved the first one. Now the second thing is that you take the conjugate of this bar you are seeing on it now is just to tell you to take the conjugate. If I to take the conjugate, just put a line across it and you change the line in between. So x2 plus s1 plus s2, then instead of positive here it will be negative because you are taking the conjugate, minus I y2 plus this. So that by the time you open the bracket now, you can now rewrite the expression, collect the z1 and also the z2. So you have this. So if you do the multiplication, the same procedure. In the multiplication part of it is just the same procedure. This one times this one, you take the conjugate. By the time you multiply, then you collect the like terms, then you apply the conjugate, you have your result. So now let's look at the last question there, which says that you should find when z is equal to a plus ib, then you should take the inverse of z now. So which means it should be 1 over this now. So if you have this now, this is denominator. You know, in sort, when you have something like this, you have to multiply the numerator and denominator by the conjugate. So this is a plus ib, so you multiply by a minus ib up and down. By the time you do that and you collect the like terms, you have this expression which satisfy this condition stated in this problem, that we should show that z bar, I mean 1 over z is equals to this, and this is what we have put here. So any questions? Any questions? Do you have any questions? Okay. If there is no question, so now let's go to today's topic itself. So today we are supposed to discuss sequence and Cauchy sequence. So the question is, what are sequence, or what is sequence? A sequence of complex number is a function from the set n of positive integer into C. That is, where you have a set of integer number in n. Now they move, those integers cannot be moved into C now, just like a room, a building and a room. the whole building, it has about 10 rooms. So the rooms now are just the set. Then inside it, you have the rooms. So we use the notation of Zn such that n is an element of capital N. The small n is an element of capital. So in this case, capital N now is the building and small n are the rooms inside the building. So or we can simply say that this now to denote a sequence index is not unique. So an example is that if you have Zn to equals to n all over n plus I. So the question is that we can show that the modulus of Zn minus 1 is equals to 1 over the square root of n squared plus 1. So let's see how we can solve this problem together. So I said the solution now. Zn is equals to n over n plus I. That was what was given to us. Now, if you want to apply this now, it will be minus 1. So this now, the whole of this minus 1. You take the common factor, the denominator, which is this. By the time you simplify this, you have this goes here 1, and then 1 goes here 1, 1 goes in this is n plus I, then times 1 to give you there. By the time you open the bracket here, this and this will cancel now. You have minus I over n plus I. So now, Zn minus 1 now will be ni over this. So the modulus now will now be the modulus of this, which is equals to, because we know that minus I is equals to minus I square is equals to minus 1. So but by the time you take the modulus now, the negative will go. So we have this. So since I said since I square is equals to minus 1, so automatically here now we have this to equals to what? 1. So now if you proceed and say that n plus I is equals to this now, the modulus of this now, we can write it in this form, just like multiplying the two together. Then if you simplify it, you have this, and eventually you end up having n squared plus 1. So you now realize that the modulus of Zn minus 1, this is now equals to 1, which is this we have established here. Then the modulus of this now is equals to this, which is equals to this. Hope this is clear. So now that is what we call sequence. Now let's look at Cauchy sequence. So a sequence is called a Cauchy sequence if the terms of the sequence eventually all became arbitrarily close to one another. That is, given epsilon, which is greater than 0, there exists n such that if m comma n is greater than n, then the modulus of am minus an will be less than epsilon. So the properties of Cauchy sequence now. 1, any Cauchy sequence is bounded. So if it is not Cauchy sequence, it will not be bounded. 2, now any convergent sequence is a Cauchy sequence. So any sequence that can converge, they are known as Cauchy sequence. Now let's look at the proof now. Say if a of n tends to b, then given that epsilon is greater than 0, like you have here, choose n so that if n is greater than capital N, we have this now, like you have here, this equation here. Then if m comma n, we have modulus of this, then it will now be am minus beta, because that is the point, less than am minus beta, then plus am minus beta less than. You can see that we have introduced 2 of this now. So that leads us to this now. So this is a proof of convergence of a Cauchy sequence. Now the third thing here is that a real Cauchy sequence is always convergent. When you have a real Cauchy sequence, they are always what? Convergent. So any questions so far?
What does that mean, sir?
Yeah. Good afternoon.
Good afternoon, sir.
Yeah.
The last point.
Late.
Yes, I have battery issues. Yeah. So.
Okay, I'm listening to your question.
Okay. The number 3, a real Cauchy sequence is convergent. What does that mean, sir?
Okay, now what I'm trying to say is that, we have the real and the imaginary. I get me now. So if you have
yes, sir.
Sequence now, they are always convergent. That's the meaning. Just like, when you draw a kind of a Cartesian coordinate, are you getting me now? If you draw a Cartesian coordinate, you have negative and positive. Are we together?
Yes, sir. Yes,
I
sir.
get my point. So now you can move to the negative. You can also move to what? To the positive. Are we together? But in most
Okay.
cases, the positive converge fast, which are real.
Okay.
Why the negative diverge? Is that taking?
Okay. Is it in terms of addition?
Yes.
Okay.
Is that taking?
Okay, sir. Is there like an example to show?
Oh, I don't have an example on this slide, but I can give an example in the next class.
Okay. Okay, sir.
Is that taking?
Yes, sir.
So I will give you an example in the next class, but I don't have an example on this slide today.
Okay.
So because you
But,
came,
but sorry, sir. I saw when I came, I saw something about polar coordinate. I don't know
yeah,
if
polar coordinate, yes,
you talked about that.
yes,
Okay, you
this,
even talked about limits. Wow.
yeah. I will send you this slide immediately after this lecture, or I can drop it here. The problem is that I realize that if I use the platform uh, on the course web page to send email, I don't know if students receive the mail or they don't receive it.
Okay.
So what I did this afternoon was to just copy all the student email address and send directly from our email box.
Okay. Okay.
Are you getting me now?
Wow. Yes, sir.
So that's the problem. But I will have sent this note earlier on, but now immediately after this lecture, I will send the note using that email address.
Okay, sir. But somehow I would like to know more about this. Somehow I want you to explain this polar representation
As you
because
explain this concept, Abi, okay.
yes.
Now what I'm trying to say is that when we started the class, we defined the complex number,
Yes.
Abi. So when we define the complex number, we said z is equals to x plus iy, Abi.
Yes, sir.
Now that is in a Cartesian coordinate, but if you want to move to the polar coordinate now, z is different. Z is written in this format,
Okay.
and the question now is that what is the value of r and what is the value of theta in this expression? So now, last week I told you that you can find the modulus of z. I've discussed that also this when I started the class. This is
Yeah.
concept about the modulus.
Okay.
So when I give you the notes, you see everything there. This is the concept about the modulus. So this is z, which is the modulus now, and this is arctan z, which is theta, which is well splitted, well explained here now. So this, which is the modulus of z, is now our r. I get him now, which goes into this expression. And this theta is the argument of z, which is this. So now, the whole of this now, exponential I theta, we can write it in this format, in polar coordinate.
Okay.
I get him now. So
Yes, sir.
next week now, the next thing we are going to be discussing starting from next week, we are going to be making use of this aspect, this polar representation of complex number, because we are going to be solving some problems. If you have downloaded the lecture note that I sent in the first week, you'll have come across some expression there. So in solving those problems, we are going to be using this concept. Did you get the idea now?
Okay, sir.
Okay.
Okay, sir.
So any other question? Any other question? Any other questions? Okay, if you don't have more questions, I think I have to stop this lecture.